All right, we're here in section 6.7. This is over a process called synthetic substitution, which is basically a way of evaluating a function by using synthetic division, okay? We're going to have to look at a couple of theorems to help us understand this process. And once we have that down, we'll actually be able to use this in order to find factors and zeros of a function, okay? All right, so let's start with a theorem. It's called the remainder theorem. It says if you're taking a function f of x and you're dividing it by x minus c, then the remainder from that division process is equal to the function f evaluated at c, okay, f of c. So kind of breaking this down, you take the function, if you're dividing it by x minus c, what this theorem is saying is that whatever this number is right here that's being subtracted from x in your divisor, if you were to plug that number into the function for x and then simplify, that would give you the same value as the remainder from the division process, okay? Now there's two types of division that we've looked at for polynomials, both long division and synthetic division. Notice we're dividing here. This is a linear binomial, so this is perfect for synthetic division, okay? So altogether, when we use synthetic division in conjunction with this theorem in order to evaluate a function, that process is going to be referred to as synthetic substitution, okay? So let's see how that works with the example below. I have the function f of x, and I'm trying to evaluate it at 4. I want to find f of 4, but I want to do it with this new process known as synthetic substitution, okay? So if you're trying to evaluate at f of 4, then using this remainder theorem requires you to think as though you're dividing the function by x minus 4, okay? If I'm dividing by x minus 4 and I'm using synthetic division, I've taught you, you need to set that equal to 0. You need to solve it for x, which in this case is 4, and 4 would be the number that you put in your box, right? So now you write out your coefficients from the function, plus sign, line, and then you start your process, okay? So I bring this 3 down. 3 times 4 is 12. Negative 2 plus 12 is 10. 10 times 4 is 40. 40 plus 1 is 41. I skipped. I need a placeholder in here. Skipped that, sorry. And then 41 times 4 is 164. And 164 times 4 is 656. And negative 2 plus 656 is equal to 654, okay? And this number right here is what I'm most concerned with. That remainder theorem says that the remainder from this division process is equal to the function evaluated at, in this case, 4. Okay, so we're saying that f of 4 equals 654. Okay. All right, now let's check this. We've, of course, been able to evaluate functions just by simply plugging a value in for x and simplifying with order of operations. So if I wanted to find f of 4 the old-fashioned way, I could have simply started here. Okay. Do all your powers first. 4 to the 4th is 256. 4 to the 3rd is 64. 4 squared is 16. Then do your multiplications. 768 minus 128 plus 16 minus 2. And then when you're all done, that's going to equal 654. Okay, so you might be thinking, well, why couldn't I just do that all along, that process that we just used as a check? Well, you certainly can, but you're going to see with some future examples, once we get into a second theorem, that this synthetic substitution can be really helpful depending on what we're being asked to find. Okay. All right, so now let's segue into a second theorem. This is called the factor theorem. All right, and it says for a function f of x, x minus c would be considered a factor if and only if f of c equals 0. All right, so think about that theorem in conjunction with the remainder theorem. If we're saying that f of c equals 0, then we are basically saying that f of x being divided by x minus c has a remainder of 0 by the remainder theorem that we just looked at. Okay, and I mean, this is not a new concept. In order to be a factor of a number or of a function, whatever the factor is, it has to divide evenly into the function, and that's what this is saying. Now, when you divide evenly, your remainder is, of course, 0. Okay. Now, another thing we can conclude from this theorem is that if x minus c is a factor, then that means the value c itself is a 0 of the function. Okay. So let's look at this theorem at play in an example. Show that x minus 3 is a factor of f of x, then find the remaining factors of the polynomial. Okay. Well, if x minus 3 is a factor, then we would want to try to divide that into the function. And we could do it with long division, or we can do it with synthetic. I'm going to use synthetic, so I'll set that equal to 0. X equals 3. That's the number that goes in the box. And I don't need any placeholders this time. All right, start the process. Bring the 1 down. 1 times 3 is 3. 4 plus 3 is 7. 7 times 3 is 21. Negative 15 plus 21 is 6. 6 times 3 is 18. Negative 18 plus 18 gives me 0. And that's what I'm looking for here. The fact that this remainder is 0 proves that x minus 3 is a factor. Right, because it's dividing evenly. And it also proves that f of 3 equals 0 by the remainder theorem, which means that x equals 3 is a 0 or a root of the function. So there's a lot going on just by the fact that we got a remainder of 0 in that process. Okay, so now we're not done. We've showed that x minus 3 is a factor. Now we need to find the remaining factors of the polynomial. Okay, but what we have at this point is the function f of x. I can now give you a slightly factored form for it. Okay, I know that one of the factors is x minus 3. And when I divide that from the function, what's left over is based off of these three numbers, right? X squared plus 7x plus 6 is a quadratic factor of the function. So notice this is giving me a slightly factored form for f of x. And then that x squared plus 7x plus 6, I'm noticing it factors further. Okay, it factors to x plus 6 times x plus 1. And that means that these are your remaining factors, right? Because we were told that x minus 3 was a factor from the get-go. Okay. All right, moving forward. So this example here is a lot like the previous example, except it's presented a little bit differently. Okay. It says if 4 is a 0 of p of x, find the remaining zeros. All right. Well, by saying that 4 is a 0, you're also stating that x minus 4 is a factor. So you can use that factor theorem as well as the process of synthetic substitution in order to approach this problem, okay? So this time I'd have to put a 4 in the box. Coefficients of the function p of x are 1, -6, 10, and -8. Bring that 1 down. 1 times 4 is 4. -6 plus 4 is -2. -2 times 4 is -8. 10 plus -8 is 2. 2 times 4 is 8. Get a remainder of 0. Okay. So, once again, this proves that x equals 4 is a 0, or root of p of x, as well as that x minus 4 is a factor. All right. So at this point, we're going to proceed the same way we did in the last example. I'm going to say p of x can now factor to x minus 4 times, using these three numbers, x squared minus 2x plus 2. Okay. And notice the directions. I'm trying to find remaining zeros, right? Whereas the last problem, I was being asked to find remaining factors, okay? Well, your focus at this point should be on x squared minus 2x plus 2. It doesn't factor, all right? If it did, those factors could lead me to the remaining zeros. So since it doesn't factor, I'm going to set that equation equal to 0, and I'm going to solve it either with quadratic formula or completing the square. To me, completing the square would be quicker on this one. So I'm going to subtract the 2 over. To complete the square, you would need half of -2, which is -1. Square it, you get 1. Factor. And I'm going to use the square root property here. X minus 1 is equal to plus or minus I. And looks like my final two zeros are complex zeros. Okay. All right. One final example. This is a bit of an application here. So we have a function v of x here. It's a cubic function, and it represents the volume of the rectangular prism that's pictured below. And we'd like to find the missing dimensions, okay? So volume for any rectangular prism can be found with length times width times height, right? So let's just assign the three dimensions here to length, width, and height. So I'll call this side length, width, height. And basically, based on the picture, I know the width, I don't know the length and the height, right? So what I can do is I can divide both sides by the width. That'll wipe these out. And then that means that the volume divided by the width would equal the length and the height, right? And the length and the height you can think of as factors since they're multiplying each other, okay? So based off of that, since I am taking v and I'm trying to divide it by the width, well, the width here is x minus 2, which is a linear binomial, so this process would be best done with synthetic substitution or synthetic division. So I'll put a 2 in the box since I'm dividing by x minus 2. My coefficients for v of x are 1, 7, 2, and -40. Plus sign, bring that 1 down. 1 times 2 is 2, 7 plus 2, 9, 9 times 2, 18, 2 plus 18, 20. 20 times 2 is 40. Those add up to, of course, 0. So we can say that v of x is factored slightly to x minus 2, and then based off of the 1, the 9, and the 20, x squared plus 9x plus 20. And now the focus is right here. X squared plus 9x plus 20 is factorable to x plus 5, x plus 4. Okay, so we already knew that x minus 2 was our width. X plus 5 and x plus 4 can be considered binomial expressions to represent the length and the height of this box. All right.